right? Going into the Zoomers. We got 9. Friday, I guess. Share my screen. Oh, every time I open Zoom. If you're zooming, let me know if at any point you can't hear me. Or understand what I'm saying, so we can make some kind of adjustment. Try to pull the laptop as close to me as possible, so the mic can pick me up. Can everybody hear me right now? Thumbs up.
Yes.
All right. So yeah, let's jump in. And y'all ghosted me last night too. I'm up there just talking and people just logging out. Next time, just say I'm gone. Don't just ghost me, bro. I'm in there like writing and talking to myself. That was crazy. I ain't calling no names, but you know who you are. We were working on 146, so we're gonna take, I think we did A and B. No, we did A and D. Let's do C, and let's do G. Let's do those two. So I'm gonna cut this out here. I'm working on a separate page, and then we're gonna finish up with Pka. Do this example right here on 147. That's a great example. All right, can y'all see that? Let me turn the lights off. That's how to go and change that. See, so. Probably not. I'll just zoom in on it. Y'all both have the handout, right? Is that right?
Yeah, I got it.
All right. So I apologize. I thought that would show up better, but it's not. Or I'll be teaching the call next week.
Oh, good.
Yeah, we're gonna make it work though. Yeah. So that's what we do, we survive. What's that, 7? So we're gonna do C. You got cut off, but I'm gonna rewrite it. We're gonna do G. We're gonna go through our same steps. Asking, we're gonna show the arrows, predict the equilibrium, and explain why one acid is better than the other. Be it the conjugate acid or the starting acid, doesn't matter. So so that's my acid, and then my base is OH minus, it's a hydroxide ion. It's got 3 long pairs. That's what it's like. Right, negative, and then let me draw the bond. I want to see what happens. All right. So we're going to show the arrows for proton transfer. Always, same thing, always from the base, proton, and I'm going to break the hydrogen bond like so. Give it back to the atom that is bonded. Never, that never changes. All right, so on the other side, what do we get from that? And let me not put that arrow, we put a box, but we don't get it. What do we get from that? What 2 things do we get? We get a conjugate base and a conjugate acid, is that right? What does the conjugate acid look like in this case? Go ahead, you can put it up. Kadir's gonna put it on the board and I'll write it on the page. So we're looking for what the conjugate acid is.
I'm going to draw the conjugate base first, or conjugate acid?
That's fine. You can do the conjugate base. So the conjugate base, I think I talked about this last night a little before the feed went down. The conjugate base is the acid after it's given up its proton. Excellent. So it looks like this. I'm gonna just steal this right here. This is the conjugate base. Electrons in, boom, that's my conjugate base. It's important to understand how to get from the acid to the conjugate base and vice versa. And then the conjugate acid is the base plus that proton, which is going to be water. I'm going to write it out. Is that right? Yes. And pKa of water we already did is 14. That's what we've been using, so we're gonna keep using this. pKa is 14 of water. We need the pKa of benzoic acid. We need somebody to look that up. All right, benzoic acid.
Oh,
yep. Just take the YL out, put O in. Gotcha. Oh, that's it. Benzoic acid. Somebody look that up and unmute and tell us what it is. If you would. You gotta hurry, Michael is
4.2.
10G out. Say again.
4.2.
4.2. All right, good. Now, with all this information, we can do a lot of stuff now, right? We can figure out the equilibrium. Is that right? We can figure out which acid is more acidic.
This got me there. I'm sure.
Yeah. It's on the other side. Yeah, you're right. We can figure out which acid is more acidic and how many times more acidic. And we can figure out why the pK of one is better than the other or lower than the other. So let's do that. Yes, I am. All right. So which way is the equilibrium going to shift? Oh, which way is equilibrium going to shift? Towards the product, because in the product, the conjugate acid is the weaker acid. Is that right? So it has a pK of 14. This has a pK of 4.2. So the equilibrium is going to slide this way. Anybody not following that? Equilibrium favors the weaker acid. So benzoic acid is a better acid. How much better? How do we determine that? We're just gonna keep driving the same points because we're trying to reinforce that. How do we know how much better of an acid benzoic acid is than water? How many more times acidic is benzoic acid? How many times more acidic is benzoic acid than water? Okay, all right, so delta Pka is 14 minus 4.2 about 10.2. So we can say roughly 10 times. So there x is 10 to the 10. Right? Or 10 billion. All right, 10 to the 10th times more acidic than water. Now we can answer this question. Why is benzoic acid a better acid than water? How are we going to do that? When we say why, not how much, but why?
Acid.
Yes.
So even more residence than water.
Well, not water, because you're comparing the basics.
Okay.
So it's this versus OH minus, wherever it is.
More residence than what's fine.
Yes.
That's probably pretty much the main point.
Yeah.
It's also,
That's the only point.
that's,
It's stable, well, not the only, because let's look at the two conjugate bases. So let's test that question. Why benzoic acid?
they're gonna say it's an aromatic. I know, that's the main point.
But the aromatic contributes to it because it adds induction. That's right. So let's look at it. So the conjugate base, we have OH minus. And then we have the benzoate anion. Back to hydroxyl. All right, so what we're comparing, anytime we ask why one acid is better than the other, what we want to do is compare the conjugate bases. So we're comparing OH minus, which is the conjugate base of the water, and then benzoate, which is the conjugate base of benzoic acid. So the Y is answered by Ireland. Right? So in each case, both oxygens are sp3 hybridized. In both cases, so that's not an advantage. Both have the same electronegativity, same size. Following, anybody not following that's zooming?
I have a question. You say you only do that when the pKa's are what?
Say that one, I'm gonna turn my volume up some. Say that one more time.
You say you only do that when you only compare the two when the pKa's are what?
Yeah, when we want to know why.
Oh,
one
okay.
is better than the other. Then we look at the conjugate base.
Okay, so we only do that if they're asking for that within the question.
Yes.
Okay, thank you.
And by they, you mean me, because I'm going to ask you. So yeah. All right. So when we look at the benzoate anion, all right, you see immediately that you can do resonance. Is that right? And you have an aromatic ring. So that aromatic ring, ooh, it's not showing up. So the aromatic ring is actually inductive, right? It's inductive. We call that, if it can do induction, we say that this electron will draw it. And not any ring, but the aromatic. It's got to be an aromatic. Right? So what we can say when we compare those two is that benzoic acid is a better acid because its conjugate base is stabilized by resonance and induction. That's how we answer that question. I'm abbreviating this. So the conjugate base is stabilized by both resonance and induction. All right, questions about that? All right, let's do the other one. I'm gonna turn y'all loose on this one for about 3 minutes. What do we say, G? We're gonna do G. All right, so for the next 3 minutes, if it takes you that long, I want you to go through the same steps. Let me write out what, because this is a formic acid, so I'm gonna write that out for you. So this is the acidic proton plus back. This is my acid, my base. Right? I want you to go through the arrows for proton transfer. I want you to write the products and then predict equilibrium. And then we'll do the pKa stuff together. So put the arrows in, write the products, and predict the equilibrium. So we need somebody to look up the pKa for formic acid, and we need to look up for methanol, which is going to be conjugate acid. I'll just write this. Right? If you get stuck, ask a question. So you have to look up the pKa for formic acid and for methanol. Your alcohol is going to be somewhere between 10 and 17. So even if you don't have a chart, you can estimate the pKa of a basic alcohol like methanol to be somewhere around 16 or 17. Anybody got the pKa for formic acid? 3.75. Good. Douglasville on the map. Killing it. 3.75. So we're gonna say that the pK of methanol, I'm gonna say 16. Is that what you got? Something close to that. Right? What about those of you who are here? Anybody got the products yet?
Got them as in like written them out?
Say that again.
What do you mean by got the products?
Yeah, written them out, yeah.
Oh, yes.
You wanna, can you annotate your screen? Do you have that function on Zoom?
I can see.
Yeah. See if you can annotate and write them in for us.
I can.
You can't?
I can.
Okay, go ahead.
I don't remember what the first one looked like, but I think it was like this.
Okay,
I don't remember what goes over here, but it was this.
H.
Is it H?
On up, yep.
Okay.
You must be using a stylus.
I am.
Wow. You moving and grooving.
Thank you.
What's the conjugate acid?
I don't remember what it looks like. Give me a second. Let me pull up my screen. There it is. I see it. Okay. So it's gonna be, oh, let me turn on annotate. CH3O and then H.
Okay, great. Y'all got here, Mike.
That's exactly what
It's okay if I call you Mike.
yeah, that's fine.
Okay, thank you. Who was that?
Medea Watson.
Thank you. All right. So this is the conjugate base. I know y'all not gonna see this when I write it on the board, but I'll write it on the paper too. And this is the conjugate acid. So that's methanol, which has a pKa of 16. So that's this conjugate base, and then this is conjugate acid. All right, great. Now we need to predict the position of equilibrium. If the formic acid has a pKa of 4.2, is that what you said, Mike? 4.2, and then methanol has a pKa of 16. Which side is going in that reaction is going to be favored? Product side. Do y'all agree on Zoom? Right, so the equilibrium is going to favor the products because equilibrium always favors what? The weaker acid. If y'all don't learn nothing else out of this section, you will not forget that. Equilibrium always favors the weaker acid. All right, now here's the question. The latter part of this question: why is formic acid a better acid than?
Because conjugate base formic acid compared to conjugate base methanol. Maybe.
So formic acid, this conjugate base is stabilized by. Let me get rid of it. Right, the formic acid conjugate base is stabilized by resonance. That's why it has a pKa of 4.2. There's methanol, which is 16 or 17. Right. Hopefully you can see now how to connect dots. When you ask why an acid is better, you look at the conjugate base and look at factors that stabilize it. When you ask how it's better, you is that everybody okay? All right, so go ahead and if you could, Medea, clear that off and I'm gonna write it in here. And we're gonna move on. Got a couple more examples I want. So the conjugate phase, oh, we have to the arrow.
It's not working to clear it.
Clear it off. I'll clear it off. It's no problem. All right, any questions about anything? All right, let's go up to this question up here. Not a hard question, but it's a detailed question. Right here, 147. So it says the following compounds are listed in order, an increasing order of acidity. In each case, the most acidic proton is shown in red. So you can see here that they're giving us the proton that they want to think about as far as acidity is concerned. Right? So those are the protons that are given to us. And we're going to cut this out, put on another page so we can zoom in. All right. So let's answer the question. It just says, okay, first thing is to show the structure of the conjugate base of each acid. Why is it asking us to do that? Why do you think it's asking us to show the structure of the conjugate base? When we want to know why one acid is better than the other, what do we compare? The conjugate base. So it's asking us to show the conjugate base. I'm going to redraw each one of these as the conjugate base. Don't worry about the aromatic part, the double bonds. Those are interchangeable. So this is the conjugate base here. Conjugate base on the next one. Right up here, nitrogen already has one lone pair, so in the conjugate base is going to have two. Then over here, all right, so those are 4 conjugate bases, and we can see the pKa's up top. Okay. pKa here is 25. All right, here's 23, 8.8, and 4.2. So let's answer the questions that they're asking. It says explain why X is a stronger acid than W. Not by much. It's only 100 times more acidic. Is that right? How did I get to that conclusion that quickly? If I say it's 100 times more acidic, that's 10 to the second, right? And we look at the pK, you just subtract them out. But so that's more acidic, yes. Not much in terms of pKa, but on a molecular level it is. So the question is why? Why is X a better acid than W? Judging from the pK, what are we going to employ? Right? We have a system for working through these, don't we? Right. We look at the hybridization state. We look at whether there's induction present. We look at whether resonance can happen. We look at the electronegativity of the atom. and then the sides. All right? So we're comparing W, which is this one. What's the hybridization state of oxygen and carbon in each case? I need to zoom this on. They're both sp3. All right, so for that one, hybridization is not an advantage. What about induction? Are there any electronegative atoms or functional groups close by that are bonded directly to that site or close to that site? They both have an aromatic ring, which is inductive. So that's not an advantage. And then can they both do resonance? Yes. This one, this, right. So both can do resonance. Both have an aromatic ring, which is inductive. Both are sp3 hybridized. Right? So what are we comparing now? Size and electronegativity? That's what's left, right? So when, in this case, no. Man. All right, let's go. That's my fault. But the same thing applies, right? That's X. And that's what. So hybridization, induction, they can both do resonance, yes. So that doesn't change. Now we're looking at size and electronegativity. So when we're comparing those two things, we're looking at the atom where the charge is, nowhere else. And this is which one is going to show up. So here we're looking here at carbon, we're looking here at nitrogen. Which atom is more electronegative, carbon or nitrogen? Nitrogen, right? Because the electronegativity increases left to right, bottom to top across the periodic table. So nitrogen is more electronegative and it's actually bigger than carbon. It has a larger atomic radius. All right, so for X and W, W is better. Because how do we say that? The conjugate base is stabilized by what? I'm just gonna forget ENX. Stabilized by. So that's what negativity and X and W. So you, yeah. And it's bigger. So because electronegativity and size, let me finish that sentence, stabilized conjugate base.
Now, with atoms with more electronegativity, they have a large atomic radius?
Not necessarily, but in most cases, actually the answer to that is no, because carbon is at the top of its column, and it's more electronegative than silicon and the other atoms underneath. You understand what I'm saying?
So when we're doing size, are we looking at just pure like atomic
radius?
Atomic radius.
Mm-hmm. And nitrogen, so atomic radius goes left to right and top to bottom. Yeah. So nitrogen is to the right of carbon. So it's bigger. Yes. Now, there's some specialized case, like when you compare nitrogen to oxygen, oxygen is actually smaller than nitrogen, which is weird.
Okay, that's interesting.
Yeah.
I also have a question about I noticed with the bases right there,
Mhm.
there's 1, 2, 3, and then there's two sets of lone pairs around the nitrogen.
Yes. So, yeah, because up here, whenever nitrogen is in its natural neutral state, It can bond 3 groups and it'll have a lone pair.
Okay,
But they don't show the lone pair here, but it's there.
okay, so,
And just like over here, you got 2 lone pairs on oxygen, and over here, 1 lone pair on hydrogen.
okay, okay, I got you.
Yeah, good question. All right. Let's do the next one. It says explain why. Let's make sure we get the right one. Is a stronger acid than C. So we're going to compare. This is C down here. This is Y, right? So we're going to compare. Actually, no. It says in the second question, why is Y better than X? So let's compare those two, Y and X. So if we go through hires, the charge is on the same atom in both cases. It's on nitrogen. So hybridization and size and electronegativity are all the same, right? Is that right? Because it's on the same, the charge is on the same atom. Hybridization, electronegativity, and size, because it's on the same atom, those don't change. So there's no advantage. Now we can look at what? Induction and resonance.
Yeah, for sure.
All right. Can I do resonance on Y?
Yeah.
I can, right? I can take this pair of electrons and do that. That. So they both can do resonance. So what's the difference? I think you said it the other day when we were leaving, right? About oxygen being electronegative.
Easy, it would be induction.
Yeah, because oxygen right here,
Yeah.
because that nitrogen is neutral, I mean, it's negative. Oxygen is, it's a great donor if it's next to something that's electron poor. If it's next to something that's electron rich, it can act like an inductive, it has inductive properties because it has a electronegativity of 3.5. So it's right underneath fluorine. It's the second most electronegative atom on the periodic table. So this oxygen can actually do induction. Right? It adds some induction, like a vacuum cleaner, pulling some of that electron density from around nitrogen. So how do we answer that question about Y, which has a pKa of 8.8, and X, which has a pKa of 23? How do we answer that question? Y is a better acid than X because what?
It's conjugate basis to stabilize resonance and induction.
Conjugate base, excellent. It's stabilized resonance and induction.
More than X.
More than X, yes. So we can say that for this. The conjugate base is stabilized by resonance and induction. So Y is conjugate base. That's what you're looking at, right? X and Y. Everybody okay online? Anybody not catching it? Or we have a question? You can always unmute, even if I'm talking to the people in the room, you can always unmute and ask a question.
So I have a question.
Come on.
So it's a possibility for one to be stabilized by 2 of the hires?
Yes, absolutely. Or more.
Okay,
Yeah, yeah. Sometimes you might
So-
have more than one of those. You might have 3 of the 5 factors contributing to stabilizing the conjugate base.
okay. So if we have a question like this and it says explain why,
Yep.
you know,
Tell
well,
everything.
okay,
Yeah.
okay,
Tell as much as you can.
okay,
Because the more stabilizing factors you have present, the better the acid is going to be, and the more stable the conjugate base is going to be. All right, let's do, we got, I'm fast, so much faster when we do this. We got 5 minutes left, so let's do the last question. Explain why Z is a stronger acid than Y.
First glance, you would think that Y has more resonance to show you the Z, but
Well, it can only do the resonance that's shown over here, right? When you push the electrons into the carbonyl.
Yeah.
but they can both do that. Now, here's the question.
Oh, yeah, they can. But
Yeah, they can both do residence, Y and Z. For those that are on Zoom, this is Z and this is Y. These are what you were comparing in this last example. The acid for Z has a Pka of 4.2. The acid for Y has a Pka of 8.8. So what is it about Z that stabilizes that more than Y? So now we get into some nuance.
yeah, the main difference.
Yep,
So it might be a little more technical.
So oxygen is more electronegative in this case. So we can say that for the last one,
The main difference.
comparing Z and Y, yes, that Z is, the conjugate base for Z is stabilized by what? Electronegativity, that's right, and what? Resonance, and resonance.
Resonance is like it's oxygen, nitrogen is larger. Does it go?
It is bigger,
This one's-
even though it's an anomaly.
Okay.
It's not, it doesn't fall into the natural progression of atomic radius. It's actually kind of like a outlier.
Okay, yeah.
It's weird.
So does the atomic radius go? It decreases
In general,
or it
increases from left to right
It decreases.
and top to bottom.
Oh, it increases from top to bottom?
Yep. As you go down down a group, the atoms get bigger because you got more electrons.
I was gonna say.
So you got more shells,
Okay.
right? As you go across, same thing. You get more electrons, more shells, the atoms get bigger.
Okay.
But it's weird with nitrogen and oxygen. Nitrogen does actually have, it's about 70 picometers bigger than oxygen. I think it's like 160. Oxygen is like 90 picometers.
Okay.
It's weird. Gotcha. But I think part of that is because of the electronegativity, because oxygen can pull those electrons closer to its nucleus, so it's a little bit more dense. But to answer the question, about Z and Y, Z is a stronger acid than Y because the conjugate base of Z is stabilized by electronegativity and resonance, right? That's a lot of words, but one thing about organic, if you can speak the language, then you can do the work. Right? That's one of the things as a professional that you're gonna be judged on is how you speak the language. If you go to graduate school or professional school and you're in a medical school and you call the bicep that front thingy, they're gonna laugh at you. Yeah, you understand what I'm saying? You can't speak the language, you're not gonna be respected by your peers. So that's why we talk in terms of chemistry. We can make it practical, but when we answer the question, we have to talk in organic language. So we say it's stabilized by resonance and induction, and that's what makes one acid better than the other. Are y'all following online? And I know I see y'all's face. I'm following.
Yes.
Yeah, so you gotta talk the language. It's one thing to make it practical and explaining how it works, but when you get ready to explain it to a general audience, you gotta be able to switch up and speak the organic language as well. So we're gonna stop right here. I forgot to post notes and videos on Wednesday, but when I get to my office, I'm gonna post both sets of notes from today and Wednesday and both videos. And the test will be open in about 20 minutes. I got it set to open about 11:30. You'll have between today and Sunday to take it and finish it. You can stop and start. You don't have, it's not timed and you don't have to take it all in one sitting, but you gotta finish it by Sunday. All right, any questions? Everybody good? And is the volume cool on Zoom? Like, can y'all hear me clearly?
Yes.
Yes, we can.
All right, perfect. All right, I'll see y'all on Monday, God willing. Y'all have a great weekend.
You too. Have a nice day.
Okay, take care.
Dr. Wilson, you know this stuff, Same, put our